Hey guys, and welcome to a new video in this computer vision tutorial. In this video we're going to talk about camera geometry and how we can calibrate a camera. We're actually going to implement a camera calibration and do some examples with some images that we take in and then calibrate our camera on those images, and then we remove the distortion that there is on our camera. But first of all, we need to know a bit about camera geometry and how we can use that to estimate where object is in our image, and also how we can use that for camera calibration. So first of all, I'm going to show you this camera pinhole model as I showed you in the first video as well, where we have these three coordinate system, where we have the world coordinate system, and we have the image coordinate system, and also the camera coordinate system. And then we have this principal point here in the middle of our image coordinate system, which is C subscript X and C subscript Y, which is the location of the optical center. So the optical center is where all the lights get hits in our principal point, and then we get a point in our image coordinate system that corresponds to a point in the real coordinate system. So we can see down here on the picture that this point here, X, Y, Z, in the real world coordinate system, it can be projected to this point here in the image coordinate system, which is the same that we can see over here. So we have this point here, UV, on our image coordinate system, and then we can scale it by some factor W here, and it corresponds to the world coordinate system, the world coordinate point over here, X, Y, Z. And then we have some matrix that we multiply with our point in the world coordinate system. So the matrix here we're multiplying is a scaling factor, and is the focal length for the X and Y direction. So these can be different, but in most of the cases these two values are just equal to each other. So the focal length can be considered as some kind of scaling factor from the real point, and then we can scale it by some factor and get it to our image coordinate system. So we're also going to talk about some camera specifications from the last video as well, or the first video, where we have this different kind of sensor types, where we have the CMOS and CCD sensors, where most of the times we're just using the CMOS, and it's just the standard standard sensor. So we can also have this sensor size that is variable, and we have a resolution for our camera, so how many pixels our camera takes. And we also have this focal length here for the lens. So the focal length is the focal plane here, the length from the focal plane to the image plane, where our image is actually getting projected to what we see through a lens. And we can also have this aperture range here, which is WD, which is the length from the focal plane to the object that we see with our camera. And then we can, from that, we can calculate the F of view or the field of view with this sensor size here, and then the distance or the length from the focal plane to the object, and then we divide that by the focal length. So if you want to calculate the field of view, you can use this formula, or if you want to calculate one of the other values here or variables, you can also just calculate for that if you already knew the field of view and some of the other parameters. So we can actually use this for using camera geometry, where we have this focal point where all the lights get through the lens here, and then we have the image plane here on the back, and then we can actually find some point here in the real world coordinate system, and then it will be projected on the image plane here. So we have this origin here, which is 0.0, and then we have the image plane here, as we can see here. So this is what we saw on the first slide with the pinhole camera model, and then we have this C-axis here, which is optical axis. So this is the zero value, or the middle point of a field of view. And then we can have this distance here from the field of view, from the center of the field of view to one of the boundaries from the field of view. So this this line here could be the field of view to the right, and then we can actually find points here and try to estimate how far they're away from the optical axis here for points in the real world, and then find it in our camera and try to estimate the angle towards that object in the camera. So we can also if you have camera geometry here, we talk about if the global coordinate system is not located in the camera, which is often the case, because we don't have like the global coordinate system is not in the camera as we saw in the first slide. We have like some global coordinate system where there's some points on, and the camera had a coordinate system for itself. And also if we have several cameras in our setup, like we can't have the global coordinate system in the camera. So we need to have some different kind of like matrices that we can use also for our camera calibration. So we're going to use all these values here in our camera calibrations to like calibrate our camera to remove the distortion. So we have this Q subscript I here, which is equal to this A here, which we're going to talk about what it is on the next slide. And then we have this rotation matrix here and the translation matrix here, and then we just multiply that by like the camera matrix, and then we get like our new global, like our new camera coordinate system that can be projected to like the world coordinate system, and we're going to use this for calibrating our camera. So this P matrix here with these values here are like actually like the camera matrix that we're going to calculate to like calibrate our camera. So it just contains this A matrix that we're going to talk about in the next slide, and then the rotation and the translation here, and then we get like the camera matrix. So we also have like these internal parameters when we're talking about camera geometry, and the internal parameters here is this A matrix here. So we have this focal length here, and the F here and the F here, and then we have some alpha that is a scaling factor that we can that I'm going to show an example on the next slide. So let's say that our image has some distortion in it, then we can have like then it's not like all the lines are not like really that good, and some of them can be like distorted, and they could be like scaled by a factor of alpha. And we can also have like some delta values for the x and y coordinates. So we have like, for example, we have like this principal point coordinate here, and it is like to account for offset in the coordinate system. So this will be like this delta x and y. So let's say here that we have like some offset in our coordinate system, and we have like an intersection with the optical axis here, and then we will have like this distance here would be like the offset in the x and the y direction. So we can also like take that into account with our like A matrix here, and so we both like with this A matrix we both like account for the scaling and offset in our image, and also like the offset in the actual like coordinate system from the like the intersection with the optical axis. So I'm going to show you the next slide here to like get a better understanding of like what this screw and aspect ratio is, where we talk about this alpha value here. So we use this screw and alpha and aspect ratio to like account for non-square and non-rectangular pixels. So when we want to like calibrate our camera, like our goal is to get these non-square and non-rectangular pixels. But we can see that we can say that when we get in an image from our camera where there's some distortion on, like we don't have this non-square like these squares and rectangular pixels, then we will actually like get some like screwed as like squares and rectangles, so they're not squared anymore. So we have this alpha value here that just like it just says like how much it is like screwed from the original point, or like from like being optimal square, and the slope here will be this beta divided by alpha. So we can use this as well like to take into account when we have this A matrix here that we're going to use for our camera calibration. So we can like try to account for this screw here. So we try to remove the distortion here in the camera and when we're calibrating it. So we also need to talk about like this field of view, where like the field of view is like how much we can see with our camera. So we can see here that we have this projection center here, and then we have our image plane here, and then the field of view will be the angle, or like how much we can see with our image, like on our image plane. So this could be like this dot here could be like our camera, and then we have the field of view with these two dotted lines here, and this will be our field of view, and then this will be like the optical center axis, which is the middle of our field of view, and then this angle here would be the field of view, like how much we can see with our through our camera lens, and then like the half here would be like the field of view divided by 2, and then we can find like if we know like the length up here, like the length of how much we can see with our camera, and the length of from the camera to like the depth of the camera, like how long we can see, then we can actually like calculate the field of view, or if we knew the field of view and we knew the length up here, then we can actually like calculate how long we can see with our camera in the image. So we can use this for camera geometry as well, where if we want to like estimate like where some point is like where some point is in the image compared to like the center axis here. So let's say we had a point here, then we can actually like use this optical center here and the length up here. So the length from here to here would be like the half of this length up here, and then we can estimate where like the angle like or the displacement from the center here to like the point in our camera, and then we can estimate that angle to the object that we can see in our camera. So we can use this to like estimate angles and also like estimate how far away that object we have detected is. So it can be used for a lot of different kind of things, and also like it's just good to know like basic stuff about field of view when we're going to talk about like camera calibration as well. So before we're going into like camera calibration, we need to talk about like distortion for different kind of camera models. And first of all, we have this radial distortion, which is like it is symmetric from the optical axis, which is in the middle here, and then it can change the magnification like the farther we get out or like the closer we are to the optical center. And to the left here, we have this barrel distortion, which kind of looks like the fisheye effect in our camera. And we can also have this pinhole distortion, which is like the opposite of the barrel distortion. So like the lines here are not like, they're not straight lines here, and they get like, they have like this curve here in the sides. And when we try to like calibrate our cameras, we try to like remove this distortion from our images, so we don't get these like curved lines here, because we want straight lines if we want to like calculate some length or do some object detection that like needs these straight lines in our image. And these like camera models distortions are like caused by the lenses in the camera, and also like sometimes we on purpose use fisheye lenses to get like a wider field of view, and then we can just like remove distortion or like calibrate our camera in code. And then try to like remove some of the distortion that we get from the fisheye camera. So an example of radial distortion on an image, it could be like something like this, and we can see that if we want to do some recognition or something else or some other operations on our image, we can see that our image is just kind of like destroyed if we have this radial distortion. So we need some different kind of methods to like try to like remove this radial distortion with first calibrating our camera. Could be one of the solutions to like remove some of this distortion. So we also talked about like this tangential distortion, which is like an uneven magnification from one side to the other. So we can see down here to the right that the magnification from one side to the other is like it's uneven. So it's not really like, it's not like Baron collection where it was symmetric on the like the center, like the optical center, and the tangential distortion is caused by like the lenses are not parallel to the image plane. So we can see down here that we have the image plane here, and then we have like the camera sensor here or lens, and it is not parallel to the image plane. Like the lenses here are not parallel to the image plane here, and that will cause tangential distortion, which we can see like over here what it is. So now we're going to talk about camera calibration. Before I'm going to show you how to implement it in OpenCV and actually like do camera calibration on images. So when we're doing camera calibration, we're using multiple images. So we need to like have a known object in our image. It could be like one of the most used examples is this chessboard here, where we have the chessboard that we're trying to that we know like the length is between all squares, and we know the squares, and we know how many squares, so we know the object that we're calibrating our image on. And then these images here, we have different positions for them. Like we could have them like rotated and translated around in the image, and also like tilted. We also need to tilt our like chessboard in the image to like get the most optimal camera calibration. And then this camera calibration here, it computes this camera matrix that we talked about earlier, and also the distortion parameters that we're going to use to actually like remove the distortion from our images. So when we're doing camera calibration, we're just like calibrating our camera to remove the distortion that we have on our lens. So the method here we're going to use that I just talked about is the Sanks method, and it's probably like the most used one. So it tries to like estimate the homogravity to like each camera plane. So let's say we have like different kind of camera planes where we're like rotating our like chessboard around, so we get like the different kind of camera planes, and then like the like distance here, or like this displacement here from one camera plane to the other camera plane. So we try to like find some correlations between those and try to estimate these like homography to each camera planes with this Sang's method that we're going to like use in OpenCV. And it's also like a linear solution for like the pinhole camera model. And we can see down here to the left that we use this chessboard here to detect the corners of like the squares, and then we know like how many squares we have and the distances for each square. So, and then we can use that to calibrate our camera. So this is just like to show you like some of the test results from the Sang's method that he did himself, where we can see down here if we like want to talk about like how many images do we need to like calibrate our camera. And one of the tests he has is actually shows that we only need like 3 to 4 or 5 different types of like number of planes, like where we have rotated and tilted our chessboard to get like a relative good error percentage. So if we only use like 1 or 2 images, like we won't really get a really good calibration. And where like if we use like 3 to 4 or 5 different kind of number of like planes, then we get a really good camera calibration. We can actually like remove a lot of the distortion there is on our camera lens. So let's jump into OpenCV here, and I'm going to show you some examples on like how we can calibrate our camera, and I'm going to like take in some actual like images where we have this chessboard here that we are rotating and tilting and translating around in the image, and then we're going to use do the camera calibration, and I'm going to show you the result of the camera calibration as well. So we're not in the Visual Studio here, and I'm going to show you like how we can calibrate a camera in OpenCV. And first of all, I'm going to show you like the images that we're going to like load into OpenCV here, and then do our like detection on the chessboard, and then doing the actual calibration, and then in the end I'll show you the result. So like one of the images here could be like one of those here, and we have like a number of different kind of images here where they're rotated, tilted, and like translated around in the image, and then we are going to load all of these in. And as we can see here that we have this lens here where we don't have like a straight line here, so this like table here is actually like in the real world it is like a rectangle, but when we have like our lens here, it like we get this radial distortion here, or the barrel distortion here, so the line here will be curved instead of this straight line here. So if we're going to like do some estimations of like where objects are in our frame or in our setup here, like they can actually like be distorted, like the angles or like the points, pixels that we're going to calculate. So we're going to calibrate this camera here in OpenCV. So first of all, we're just importing all the OpenCV libraries that we're going to use. And then first of all, we have this glob here where we're going to like load in all of those images from the folder, like, or the directory that I just showed you. And then we have like this pattern size here, which is like the size of like the pattern for our chessboard. And then we have like these Q matrix here and the Q here, which is like the coordinates for the world. So first of all, we need to generate the checkerboard world coordinates Q, and the board has a 25 times 18 fields, and all of the fields has a size of 15 times 15. So first of all, we're going to create this array here where we have these dimensions here for the board, and also the field size for like all the squares in our checkerboard. And then we need to define the world coordinates for our 3D points. So I showed you in the pinhole model that we had like these world coordinates, and then we need like these 3 points because we have a X, Y, and Z coordinate. So first of all, we're just having this for 2 follows here running through, and then we have like the first point here, like, or the X point here is this J here times the field size. So we need the field size here for the X and Y axis. And then we don't have a Z axis in this case here, so that will just be 0. And then we create an object point for our world coordinate for all like the object points in our image, and then we store it in this object points here, a vector that we're going to use to calibrate our camera. So if you had some other field sizes, you just need to like put it in here, or if you had some other dimensions for the board, you will just change these values here. It could be like a 10 times 6 board as well, and then it will just like make world coordinates for 3D points for that chessboard instead. So this is just like to define our world coordinates for the 3D points for the given checkerboard that we have in this example here. So we also need to have a vector with our image points that we're going to use for calibration. And then we have this for loop here to detect the feature points in the actual checkerboard. So we need to find like all the corners of the squares in our checkerboard. So we have this for loop here that just runs through all the images. So we can use this for loop here to run through all the file names. And in all the file names we have all the images that I showed you in the directory and the folder. And then second, we have to read in the image and then call this find chessboard corners, because there's a built-in function in OpenCV to find like the corners of the chessboard here that you're going to use to do our actual like camera calibration. So first of all, we just read in our image here one at a time with this file names here, and then the number we are at right now. And then we convert our image to a grayscale image to like make the operations easier to do. And then we have this Boolean variable here, and it will just say one like false or true if we like found a pattern on the chessboard. So we're going to load in these images here, and we're going to like find the corners on the chessboard. And if we can find like all the corners on our chessboard, this will return true here. And then we can do some other different kind of things if we found the pattern in our chessboard. So this function chessboard here, it takes the grayscale image here and it takes the pattern size, which was like dimensions the -1 of the checkerboard. And then it was like these q of I here, where like our q was like this size of this was like the object points up here, like or the image points. So we have this image point here that we're going to like fill in, and we're going to use these image points here when we're going to do the calibration, and then just some default values from the OpenCV documentation here in the end, where we have this calibrating adaptive threshold, and we're normalizing the image burst, and then we're doing a fast check. So these are just like default parameters in OpenCV when we're using this chessboard corners function. So we need to use this corner subpix here to refine the found corner detections in our checkerboard. So first of all, we have this if statement here that checks if the pattern is found, because we only want to do this if we found a pattern in our image. And if we have found a pattern in our image, we use this corner suffix here, which take in the grayscale image, and it takes also like the image points, and then it takes some size, which is just like a default size from OpenCV, which is like the rest of the parameters here. So we're going to use some like termination criteria where we have this EPS and max iterations. So these are just all default values from OpenCV. Like you can play around with them if your result is not good enough, or for some other cases, or if it doesn't like work in your application. So this function here just take like the grayscale image and then the image points that we're going to use for actual calibration. And then if we found a pattern, we also want to like push back our object points here for our like world coordinates until this q vector here, where the q vector was like the points here, like the world coordinates for our checkerboard. So when we have found all the corners here and we have done all this, we can do the actual like we can draw the actual like chessboard corners on our image. So we just do this with taking our image that we want to draw the chessboard or like the pattern that we have found, and then we also give it like the pattern size, which was the dimensions -1, and we also have to give it the image points that we found with this corner subpix up here, and then if the pattern was found, which is just a boolean that is either like true or false, and then we can display our image here with our chessboard and the actual detection of the chessboard in our image. So when we have done all this here, we need to go down here and we can then calculate an error for a calibrated camera, and we just calculate this error here, and then we use this calibrate camera function here, which is the function that does the actual like camera calibration with the values and the matrices that we have found and calculated up here in the for loop for each picture. So we have these flags here, which is also just like standard values for our for OpenCV when we're doing camera calibrations, and then we have like our rotation vector and we have our translation vector, as I showed you in the slides, which is actually like matrices. So we have this rotation matrix and we have the translation matrix that we're going to use for our camera calibrations. So these are like the matrices that are talked about in the slides that we're going to like use for our camera calibration here, and some of the like the camera geometry that we went over as well. So this is like where some of the like the things we're talking about in the slides are getting useful. So we also have like this K here, which is just like the intrinsic camera matrix that we're going to like store the values where we have calibrated our camera. Then this will be the new camera matrix that we can then use for later on when we have already calibrated our camera and we don't need to do it again. Then we will just use this intrinsic camera matrix. So we also need these distortion coefficients. So these are the two outputs from the calibrate camera function down here. So first of all, it takes like the world coordinates here, and it takes the image point, and it takes the frame size. So the frame size of like the images, and then it takes like this K, uppercase K, and the K values here, which is the distortion coefficients, and the other K is some of the values that we calculated up here. And then we give it like this rotation vector and the translation vector, and then the flags here, which is just standard values again for OpenCV. So these are the two outputs that we get from this calibrate camera, and these are the two values that we can use later on when we have already calibrated our camera, and we're going to like set up this setup again. So down here, then we need to like pre-compute the lens correction interpolation. I'm not going to like go in depth with that. It is just like standard for like OpenCV. And then we like need to show the lens corrected images. So when we have done our like camera calibrations, we need to want to like show the corrected images or like the calibrated images that we have calibrated beforehand. And then we're going to use this remap function here, where we can actually like remap the image using the pre-computed interpolation maps. So the values that we have just calculated now, we want to like remap that to the image, and then we can like show the actual like undistorted image down here. So if I run this program here, we can see over here that we get the first image here, and we also get the terminal here. So we load in the first image here that we're going to apply this detection on for the checkerboard, and we can see that we actually like detect all the corners of the squares in our checkerboard here. And then when I hit escape, it will like load in the next image and do the same stuff here for like all the images that we load in that we want to calibrate our camera on. So we can see here that we're rotating and like we're translating the checkerboard here around in the image, because we want to like get the most optimal solution and calibration that we can get. So we can also see like here we tilted the checkerboard to like get a better like calibration as well, and we rotated it around as well. And then we just go through all the images here and do the calibration with this checkerboard detection function. So now we can see that it has now went through all the images, and we can see down here in the terminal that now we're calibrating the images, and then we will just wait here until I calibrate the images, and then now it's calculating the distortion parameters and the camera matrix that we're going to use. So we can see down here that we get the camera matrix here, the big K, and this is the one that we can use for like in other like programs if we have like the same camera and stuff like that. So we don't have to we only need to do this camera calibration once, and then we just use these parameters here that we calculate from this calibration. So this is the big K here, the camera matrix, and then we have the distortion parameters here, lowercase k here. So then we can use these parameters here again. But now we have these undistorted images here, and we also have like the original images over here to the left. So we can see down that here on the left we have these curves here because we have this barrel connection on our lens, and we have these curves here in our image for the lines where on the undistorted image, and when we have calibrated our camera, we can actually like get these like really straight lines here in our image, and also for the checkerboard. So this more looks like a rectangular table here where we have like undistorted our image, and we have removed the barrel distortion by calibrating our camera. And if we escape here again, we just go through all the images. I'll have to go into here. So we go through all the images again that we have calibrated, and just like to see like all of the images are actually calibrated, and we can see that we've removed the curves here for the lines, and also like checkerboard, it's more like smooth. And if we want to like calculate some distances or find some points on our table here that we're going to pick up with a robot arm, or do some other like operations on, like we get a much better result now than if we had like some distorted images. If we want to like calculate the length or like distance from this point to this point, then it is like better to have this straight line here than this curved line that we can really like, then we get a like really unprecise result. So this is like just to show you like when we have calibrated our camera, like our setup and our camera and our images actually get a lot better, and it's easier to do operations on and apply other algorithms for like processing the images. So I'll just go through all of it here, and then it just terminates when we have seen all the images that is now calibrated. So now we have calculated like we have now calculated our intrinsic camera matrix and distortion coefficients, and we have calibrated our camera with images where we found this chessboard and then did detections on the chessboard, and we moved it around. So these are pretty cool features, and they're very practical, and every time we set up a camera setup in a practical setup, we do this camera calibration to like get the best result and get the best images that we then can do some other like processing or like apply some other algorithms on. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you want to see like more of this in the future, because like these are very practical things, and I think it like they're really cool to like see how we can actually like apply these methods and what we learn in the slides, and also like some of the theory, like how we can apply that to like actual practical problems. So if you're interested in one of the other tutorials I'm doing, I'm also doing an artificial intelligence tutorial and algorithms and data structure tutorial. So if you're interested in one of those, I'll link to one of them up here, or else I'll just see you in the next video, guys. Bye for now.